Alrighty, let's go ahead and get started because it looks like the trickle is slowed to even less than a trickle now. So it gives me a great pleasure to introduce Ann Newman this afternoon. So she's somebody who we were a faculty together at the University of Pittsburgh, and looking at her CV last night, it's actually a fairly easy CV to explain. It's it looks like other than 2 years at the very beginning and 4 years in the middle, it's always University of Pittsburgh. So it's so she started at Penn State, finished her undergrad at University of Pittsburgh, stayed on for medical school, then was house staff at University of Pittsburgh, did geriatrics fellowship at University of Pittsburgh, did an MPH in epidemiology, University of Pittsburgh, joined the faculty at University of Pittsburgh, escaped for 4 years to go the opposite side of the river. So those of you that haven't been to Pittsburgh, University of Pittsburgh is kind of back here. She went the other side of the river, so probably about 5 miles away from University of Pittsburgh. Was faculty there for 4 years, then came back to the University of Pittsburgh, and then worked her way up through the ranks at Pitt, and is now the department chair of epidemiology in the Graduate School of Public Health. And so she's been a really prolific author and has over 600 publications, and more importantly has been kind of a lead faculty member, PI, co-investigator on a number of really seminal studies that have kind of shaped how we think about human aging from the 1990s till now. So without, I'll go ahead and let her speak now. So thank you, Dr. Newman.
Get a kick out of hearing what people make out of my CV. How did she do this when she never went anywhere? But Pittsburgh's a wonderful place, and I love it, and there's our beautiful skyline. There you go. And we miss you, Al. I'm still working away in Pittsburgh. So when I was asked to talk here today, one of the things that I've been thinking a lot about lately is sarcopenia, and have had a few conversations with Nick Musey about some of the possibilities of future work in this area. So I thought that it might be useful to you to think with me about why we're having such a conundrum about sarcopenia. So this is a little bit of a historical perspective as well as an analysis of the current literature to explain why it is that sarcopenia has been so difficult for people to agree about. So just to start, though, sarcopenia is very clinically relevant. It's very obvious that we have changes in body composition with age. You don't need anything fancy to see this. It's apparent to any clinician who's looking at an older person that as they age, they have less muscle, more fat, less bone mass, and the central deposition of fat. And it does have important clinical consequences with a lower volume of distribution. So if you take a drug that's water soluble and you're having more fat mass and less water mass or lean mass, it's going to change how that's distributed. And more importantly, if you have more fat mass, you're going to have a longer half-life for your fat-soluble drugs. And it's been long stated that muscle is the major determinant of strength. It's also the major determinant of resting metabolic rate. And it's that latter reason that it was stated about 20 years ago that sarcopenia is a major, major reason that people become disabled as they get older. And I'm going to show you why this really isn't so clear. I feel that from reading the literature, from talking to colleagues in different disciplines other than geriatrics who are thinking about sarcopenia in cancer patients, in surgical patients, that the confusion is increasing. It's not decreasing. There's a lot of assumption. There's a lot of carrying ideas from some key references forward that I don't think is well-founded. But anyway, back to body composition with age. I like to show this picture of a painting of the stages of life, which was a very common subject in artwork for over the years, particularly in the periods where life expectancy was very short. And you can see in this painting the changes in body composition are even illustrated here, that anyone who thinks about aging recognizes that this is happening as people get older. But there is a pattern to it where there's first a tendency to gain weight in middle age. And it's not until older age that you begin to have the loss of height, the fat mass increasing centrally, and the loss of muscle mass and bone loss. So it's a process over the lifespan. And it's only until very late in life that you see people who are really involuting, really in a catabolic state in very late life. And people have equated the idea of sarcopenia with the term of frailty, though there actually isn't really strong data on this, because both of these conditions have been diagnosed using a sort of composite variables that are related to each other in various ways. But nevertheless, I think that we can all agree that there are changes in body composition as we get older. This is a study from the 90s from Gilbert Forbes, who I'd love to meet sometime. He did this study of tracking body composition for many years in a single subject. And this is the pattern that you see, that there is a tendency for a gain in weight that can even persist in people into their 80s. And the fat-free mass isn't changing. So this is just one person, but this is the pattern. That, and it may be that to maintain your muscle mass, you do need to gain weight to preserve your muscle mass. And if you stay weight stable, as you get older, you're probably losing muscle mass. This is another picture of this from the Baltimore longitudinal study on aging. This was a paper that was actually looking at the decline in maximal oxygen consumption with exercise and trying to understand how much of that is due to this change in body composition. And it is related. Here you see a series of graphs following people and groups of people for, I think, about 20 years, and then sort of linking them all together. And you see the same pattern, that weight goes up, and what you get is a stable lean mass, and only late do you begin to see them both decline. So this is a real phenomenon. There's no, I think, question about that. But there have been a huge number of challenges for people to use this in a clinical sense. And these are the challenges. And if you want the really short version of this talk, you can just write down these things. But I'm going to go through and explain each of them in a little bit more detail. So the issues are the various methods of quantification of lean and muscle tissue, lean or muscle tissue, loss of the correlation between lean loss and strength loss, confounding by fat mass, body weight dynamics, allometric scaling, which is scaling to size, varying outcomes that have been used in the literature, not much data on longitudinal assessment of body composition change, and finally, a shifting definition over time that you'll see in the literature. Okay, so first in terms of methods, there's very good, very high-tech methods nowadays, but I submit to you that one of the best methods we still have is actually putting somebody on a scale and measuring their height. And this is a little joke slide that tells the person that it's not water, you seem to be retaining food. And I understand that problem. And here the New Yorker cartoon, most likely, of the age relating to the loss of height. And as you get older, you're losing your height. But seriously, there are methods that are really quite good. These are some of them. I should have included on here just measuring creatinine excretion for 24 hours has been used. Total body potassium was the original method that was used. Bioelectric impedance, you've heard about, they have it at the gym. Not probably enough accuracy for research studies: dual energy X-ray absorptiometry, MRI, CT, ultrasound, and creatine dilution. Most studies in older adults that are specifically focused on measuring body composition have used DEXA, which is the same test that's used for bone density, and measure the lean mass, which is actually fat-free mass, and isolate the arms and the legs to get the fat-free mass that's mostly muscle. And using this, there have been lots of associations found with disability, with mobility, with mortality, but it's very dependent on the indexing of the measure. And if you look at the literature, the indexing has been to height squared, to BMI, to total mass, to fat mass. And you have to really look for that if you're going to understand the sarcopenia literature. And the results are not always consistent, even with the same indexing. This is a picture of a DEXA scan showing how the arms and the legs are segmented off, and it's reading from a 2D picture the portion of the body mass that's fat versus lean, and it takes out the bone. There is evidence from CT scans or MR scans. I was the Pittsburgh principal investigator for a study called Health, Aging, and Body Composition. Health ABC was started maybe 20, 25 years ago and measured body composition repeatedly with not only DEXA scanning, but also with CT scanning. And the CT cross-sectional area tended to be more strongly related to outcomes than the DEXA lean mass in Health ABC, though this is not widely recognized. In the surgical literature more recently, and also in the surgical oncology literature, you will see papers where CTs that are obtained for clinical care, so if it's a paper on resecting the lung for lung cancer, well, they're getting repeated CTs of the chest, so you can look at some of the muscles in the chest wall, or in many cases for abdominal surgery, looking at the psoas muscle. And these have been shown to be associated with surgical outcomes or complications or mortality. But again, there's huge variation in how obesity is accounted for, how the density of the muscles by CT is accounted for, or whether or not height is considered. Here's some actual CT scans from the Health ABC study where you can see cross-sectionally different amounts of fat. The gray around the muscle is fat, and the pink highlighting is the intramuscular fat. And you can see that even with the same circumference of a thigh, that you can have tremendous variation in how much of the body composition is muscle, how much is fat. And what the DEXA can't tell you is it's not telling you about this fat that's marbling the muscle, and it's not telling you about the density of that muscle by Hounsfield units. Here's an example of a CT scan with the psoas muscles being outlined, taken from L4 level. And now with algorithms from CTs that are obtained clinically, these can be read in an almost automated fashion and have been claimed to demonstrate sarcopenia. So those are the methods. They're varied, but they're good methods, and I think that's not really the problem so much. Here is an issue that I think is more of a concern, and that is that there is a loss of correlation between lean loss and strength loss. So cross-sectionally, if you want to know how strong somebody is, the first thing you want to know is how big they are, because it's correlated at least 0.5, if not more, your muscle mass with your strength. But longitudinally, in old age, this does not hold up. And I think one of the best papers about this is from the Health ABC study, which I had the opportunity working with Brett Goodpaster, who was on a K Award in Pittsburgh. He's in Florida now, but had the opportunity to sit down and look at this longitudinal Health ABC data, and we were actually, frankly, pretty shocked to see this tremendously accelerated loss of strength. We see the loss in the muscle mass in the light gray bars, but the loss of strength far outstripped that. And so that assumption that sarcopenia causes disability in older people began to break down right here because we could not explain this loss of strength and subsequently the loss of function by the loss of the muscle mass over time. The next big issue, no pun intended, is the confounding by fat. So fat and lean mass are highly correlated, and I think this is really underappreciated. The fat quantity and the location of the fat over and over again are shown to be very strong predictors of disability across age, but especially in older people. And this aspect of body composition, the very negative and adverse effect of excess body fat on function, is not well appreciated in the sarcopenia literature. Now, I don't even have slides on sarcopenic obesity, but what people have tried to do is to cross-tabulate low muscle mass with high fat mass. And this seems like it should be useful, but if you look carefully at a lot of those papers, what's driving the associations is the fat part of that combined variable. And furthermore, many indices of sarcopenia that you'll see in the literature, it is not demonstrated in those papers, but the sarcopenia, quote unquote, sarcopenia indices are highly correlated with standard indices of adiposity. This shows you just from Health ABC data that I pulled out to illustrate some of these points that your lean and your fat mass are highly correlated. This is Health ABC, ages 70 to 79. This is the baseline data. You see the correlation between lean and fat in men is 0.6 and in women is 0.7. Those correlations are high, making it hard to tease out the independent effects of lean and fat mass. And here from Health ABC, we looked at lean mass, fat mass, strength, and muscle density, and we showed that when you understand the amount of fat, the density of the muscle, which is also a fat measure, and the strength of that muscle, there's no prediction of lean mass on function and on disability in Health ABC. But people have used different analyses techniques and different indices, and they have shown associations, and I'll go into that a little bit more. Yeah. People have shown associations of muscle mass using indices, but looking at them separately, the muscle mass falls out in Health ABC. Yes?
So how is using CT to make various slice filters correlate with dunking somebody in the temperate water in terms of parsing out what constitutes lean mass and fat mass?
Yeah, well, that's better understood from whole body MR.
Yeah.
So a CT is a single slice, so you have to make some assumptions about, you have to put height into the equation to add up those slices. But the CT cross-sectional fat mass and the CT cross-sectional lean mass correlate very well with a total body method of measuring body composition. So the slices are good. They give you very good data. And yeah. Yeah, but more based on whole body MR than on whole body CT because of the radiation exposure. So if you extrapolate that MR is similar to CT, then I think we can say that the CT is good. This used, looked at the DEXA measures as well as the CT measures. The muscle density comes from the CT. Yes?
The expense of strength, I don't remember how you measure it. Was it a biovector machine or?
Yeah, it was isokinetic dynamometry of the quadriceps at 60 degrees per second, which matters too. I didn't have a lot on different modalities of measuring strength, but they're all pretty highly correlated. We've done isometric, isokinetic. Okay. Anything else? Okay, this is another paper by Peggy Cawthon at UCSF that I think is an excellent example of the problem that we're having with sarcopenia. So what she tried to do was to break body composition apart by a factor analysis. And she allowed to go into the factor analysis all these measures of adiposity, body size, lean mass, fat mass, strength, thigh muscle area, and measures of function. And the factor analysis, the biggest factor related to function were the adiposity measures. A little bit less was the lean mass and strength measures, which we know are correlated with each other cross-sectionally. And then you couldn't quite pull apart those two factors. They overlapped. And it's that overlap that I think is giving us the difficulty in defining a person as being sarcopenic. So that's the fat problem with sarcopenia, and then there's a body weight dynamics problem. So as you gain weight, you gain lean mass. As you gain weight, you lose fat mass. If you lose weight, you're going to lose both. That happens in all cases. In dieting studies, you can see this. You'll see claims in the dieting stuff online that you can completely conserve your muscle mass with weight loss. You'll see claims that if you exercise enough and take anabolic hormones, you can completely maintain your lean mass with weight loss. And that may be the case with extreme measures, but for the most part, anybody whose weight is fluctuating, the lean and fat are fluctuating together. And in fact, the fat compartment varies more with weight change than does the lean. Most people will conserve their lean mass when their weight is changing relative to their fat mass, and that's what fat mass is there for. It's meant to be an energy reserve that is plastic and can increase and decrease more with weight changes than the lean mass. When you look at, again, if you look at the sarcopenia literature and claims about loss of lean mass with age, if you look carefully, most of those people have lost their lean mass because they've lost weight. And a simple scale would adequately demonstrate that they've lost lean mass. But there's a concept that I think is very important about this that I do think happens in older people, and that is a failure to conserve the lean mass as much as one would if one were younger or healthier as weight is lost. Now these are even, I know, harder for people to follow, so I'll try to go through them carefully. But from analysis that we did in Health ABC, we looked at the body composition for just the two compartments of fat and muscle in men, and then I'll show you women. Now, what do you think should happen when you lose weight? Should you lose weight in exact proportion to your starting body composition? Most of us are mostly muscle or lean mass and organs, as well as the muscles in our arms and legs. And in the Health ABC men, the average percent body fat was 32%. Now that's pretty high for men. Younger men will have percent body fat more in the 10 to 15% range, but it does go up in older men, but overall weight tends to go up in older men as well. So this is just an average of these 70 to 79-year-olds, that their starting body composition was about a third fat and 2/3 lean. When we looked at their change in their weight, their body composition before their weight changed and their body composition after their weight changed, what we noticed is that they were losing more fat than the fat they had as a proportion. So that chunk of weight that came off had more fat in it than their overall body composition. But for the people who were losing weight and for the men who were losing weight, their weight loss was not that different from their starting body composition. So what should it look like? Well, the women tended to be more balanced in their weight loss and their weight gain, where when they lost weight, that weight that was lost was far more fat, 60% fat and only 40% lean. And when they gained weight, they were gaining 76% fat and 24% lean. So this was just observationally, and Most of this was involuntary, but, and what we found as a further elaboration of this analysis, we found that this failure to conserve, this pattern, was seen in men who lost weight in a period where they were hospitalized. That was the only way that we could be sure that we probably really had involuntary weight loss. When you ask people if they have voluntary or involuntary weight loss, they will say it's voluntary if they wanted to lose weight and if they're heavy, so it's very, very biased, even if you ask it prospectively. We tried asking, we have a paper on prospective question about voluntary and involuntary weight loss in this study, and what people who report voluntarily trying to lose weight, those people are healthy, fit, active people who are concerned about their weight. It doesn't really tell you if the actual subsequent weight loss was voluntary or not. So we've really tried to figure that out, and in this analysis, what we found was this pattern of this failure to conserve was seen only in the men who were sick. And I think that's involuntary, and that's a failure to conserve. This is in the title of this paper, actually, and when it's cited, people miss the part about it being in the people who are sick. So on the whole, and the women show this better, older people have the ability to conserve lean mass with weight loss. They have that ability to do that. So some people have used this as an argument against obese older adults dieting, and I don't mean it to be that. What I mean it to be is that older adults can conserve their lean mass with weight loss. They can. Yes?
So were you able to check out the women who lost weight in the hospital situation? Did they differ from the men in the hospital situation in this regard?
Not in this analysis, but we started to get down to small numbers because the men were more likely to be hospitalized than the women. The women who lost weight, I still think that little bit of an imbalance. You see in the weight gainers that their percent fat gained is 76%. It's mostly fat, a little lean, but the loss is 40%. So I think they're failing to conserve a little bit as well. But this dynamic situation is very important to think about because some of the sarcopenia literature does not take into account that dynamic situation, which I think is strongly influencing body composition. And we have some longitudinal data I'll get to at the end that I think supports the idea that looking longitudinally at changes in people may be more useful and more accurate in saying if they're sarcopenic than a single point in time where their body fat tends to be overwhelming the other aspects of the lean mass. So in addition to these body weight change dynamics, there is a background lean fat shift that's going on with aging. What I showed you were just the two dynamic states of losing or gaining weight. The background lean and fat shift can be seen in the individuals who were weight stable. Now, in this particular cohort, and this is true, and I have other cohort studies that I've looked at, the minority of people in their 70s and 80s are stable in their body weight. They're tending to gain weight as they're less active and their joints hurt, or they're losing weight because they're catabolic due to some illness or infection. A third or less are stable in their weight. So this was first looked at with some MR data that they looked at weight stable individuals, and they saw this kind of trade-off. So the weight here, total weight, is only changing by 0.2 kilograms. So there's a little bit of a gain, but the skeletal muscle mass is going down. The visceral fat, the visceral adipose tissue is what that stands for, and the intramuscular adipose tissue are going up. So even in somebody who's weight stable, their body composition is changing as they get older in this way. And when we looked at this in Health ABC, I have both the weight loss, the gain, and the weight stable, but I'd like you to focus on the weight stable individuals. And what you see here in the men is this kind of trade-off that they're losing 480 grams of muscle and gaining actually appendicular lean mass, and they're gaining 690 grams of fat. This is a little bit of an imbalance towards more fat than lean, but it's a big difference between men and women that we saw the men losing a lot more strength and more lean mass, with the women being more stable. But this is over a 4-year period, so we're talking about grams of shift in body composition. It's very subtle in the short term, not huge swings. And here in the women, we saw pretty much an exact balance between the lean and the fat. So the next important issue about this is the problem of allometric scaling. So allometric scaling is what was done to create the body mass index. You're all familiar with body mass index, which is height, weight in kilograms divided by the height squared. So why height squared? Does anybody know why height squared? Who came up with that? Anybody know? So this was done to remove the correlation between weight and height, to try to understand obesity and then to relate it to techniques like underwater weighing, where we had accurate measures. And lots of different scaling factors were tried, and the weight divided by height squared seemed to give the best approximation by removing the correlation to height to be like a body size free measure of how fat someone is. And it actually works pretty well now that we have DEXA percent body fat and these other measures. It's actually very good as a measure of adiposity. So what are you going to do with the muscle compartment? Well, some people thought it makes sense to just take the muscle mass or the lean mass and divide that by height squared. You get a BMI of your lean compartment. Sounds pretty good. So the scaling with height squared actually also removes the correlation of appendicular lean mass with height. So that's good, because you don't want it to be how big somebody is. But the scaling, it could actually be very complex. And there's a nice paper by Steve Heimsfeld that sort of broke down all the aspects, and it's actually not exactly height squared that gives you the best fat measure. It's height to the 2.21 in men and height to the 2.1 in women. It's slightly different, and you can go to different groups that have different body sizes, and it turns out that in general, compared to whites in the U.S., blacks in the U.S. tend to have longer legs. Well, then they're going to have more muscle. So you need to have very specific, you could come up with an index for all these subgroups. You probably could come up with almost an index for every person, because everyone has different body proportions. But nevertheless, because in spite of this variation, the simple lean mass per height squared has become very commonly used in the literature. Okay? Did you have a question about that? So it turns out that this is appendicular lean mass, arms and leg lean mass, is less predictive of disability in women than in men. We know that women have more fat at every level of lean mass. In fact, this is probably the biggest difference between men and women when you're looking at biology and function and metabolism and cardiovascular risk and everything else, is that women have more fat than men. Women usually are about 30% fat compared to 15% for men. And older women can get to be 30, 40% fat or more, even if they're not what you would consider obese. If you take the average BMI of an older person, it's in the U.S. about 27. That's considered overweight. But a man and a woman can have the same BMI and very, very different levels of fat. So it has raised the question, which hasn't really been put to the test in the literature, should we have sex-specific indices for sarcopenia? Maybe not for obesity, because the BMI works well for both, but it doesn't work well for both with the appendicular lean mass per height squared. So there's no study that's carefully compared multiple scaling factors or developed very specific scaling factors for subgroups in the population, and the literature is fraught with many different indices. But this is not just true about the sarcopenia field. If you look at other fields, like in cardiology, the heart muscle is often indexed and the ejection fraction is indexed to body size. Some use surface area, many different methods of doing this, and none of them, they tend to be more traditional than they are really proven to be ideal. So it's not just this field. So anyway, this appendicular lean mass for height squared, here is its correlation with body mass index by men and women separately in health ABC participants. And this is the type of analysis that I used to do when I wrote those other papers that never made it into the papers. And I have found maybe I need to write a paper that puts these things actually out there, because I just saw it as background analysis. So I redid it, and you can see here that the appendicular lean mass by height squared metric, considered the most often used in the literature, is correlated with BMI in men at 7.5 or 6. I can't quite see it, and in women even higher, 0.85. So what you have is a measure of sarcopenia that's also telling you that you're identifying very thin individuals. They're so highly correlated that I don't feel that you're really separating out the compartment of the muscle mass as the most important factor, because muscle and fat are correlated. So you still end up with a measure of body composition as opposed to sarcopenia. So I created this other way of doing it that basically it adjusted the lean mass for both height and fat mass. And when you look at how that's correlated with body mass index, you see a less of a correlation, 0.3 and 0.2 in women. And this measure in this cohort was more closely related to function than the other measure. So this pops up in the literature, but the complaint that people have about it is that you have to know math to do it. And it may not be the best metric. I was just interested in whether you took a metric that took body composition as a whole, if you could explain function better than if you took a metric that did not include fat. And it is more related in this cohort. And this was the paper about that, where we looked at the correlation now between the appendicular lean mass divided by height squared versus what we call the residual methods. It's basically, is your lean mass lower than expected for your height and your weight. And they actually are highly correlated with each other still, but there's enough of a difference. This is the people who are low on the residual methods and the people that are low over here to the left on the appendicular lean mass by height squared. And they're identifying different people, with only about half of the people being in common in both, in the women. More correlated in the men than in the women. So again, we have this problem with the women and the men having sort of different relationships between their lean mass and their fat Another metric that was developed was to take the appendicular lean mass divided by body mass index. And the Foundation for the National Institutes of Health had a large project to come up with a data-driven consensus method, and they found that the best metric and cut point for lean mass to relate to function was this lean mass divided by BMI. And when you look at that versus the, I guess we call it the more standard method, they're even less correlated with each other. So we have these methods of adjusting that are all different, but ultimately none of them is agreed upon to be the most successful way to do it. So then there's an issue about what's the right outcome. We don't have a gold standard, so we use outcomes to say what is sarcopenia versus not sarcopenia. So function is often used. Mortality, I think is a better method because we think that this is kind of an accelerated aging phenomena, so these people should have a higher mortality rate. The problem with function is that people have now used function to define the sarcopenia, so it's used both in the definition and then as the outcome and to validate it, and that makes it difficult. And ultimately, with all these different approaches, again, it's hard to compare studies. So one of the papers that's most often cited about whether lean mass is important or not is this paper, again, from Health ABC, where we didn't use an index in this. We used the CT area, we used the fat mass areas, we put in height alone into the models, and we looked at strength versus lean mass. And the paper was initially meant that my idea would be that, well, we know strength is related to mortality, so when we adjust for these fabulous measures of body composition we have, we will attenuate some of the association of strength with mortality. And that attenuation and that amount of that association really gets at what is sarcopenia. And I was actually rather surprised by this, but we found that the DEXA measures and the CT measures, for the most part, had no relationship to mortality in this cohort, while strength had a strong relationship with mortality. And that changed the title of the paper from the findings that strength and not muscle mass. Now here you'll see a borderline significant relationship of the CT area with mortality in men. And that actually has held up in some recent analyses as well. So it's not that there was no association whatsoever, but these were reported on a standardized scale, so it's kind of telling you the relative importance of the lean mass and the strength. And the strength measure completely wiped out the lean mass and was not at all attenuated by the body composition, the fat, the lean, the height, anything else. Body composition basically did not predict mortality in Health ABC. Fat in Health ABC predicts function, and nothing predicts in body composition predicted mortality. So there's been a lot of papers looking at sarcopenia and mortality. This review divided the studies that focused on strength predicting mortality. There's various effect sizes. This depends somewhat on what units of strength you're using. Some of these with big effects are probably the upper quartile versus the lower, but the bottom line is that all the studies that are published show strength predicts mortality. When you look at the sarcopenia papers, only these few up here have confidence intervals excluding one. Only these few are statistically significant. So why would that be? Well, it could be sarcopenia doesn't matter, or it could be these metrics that are all different in the literature and in all of these papers. So another issue is whether the change or a single measure is more important. I think they're both important, but we finally looked at the change in body composition over time, and we called the paper Body Composition Remodeling and Mortality because we decided we're not going to write a sarcopenia paper. This is what I think we need to do in the field of sarcopenia is we need to talk about body composition, not isolating one compartment from the other because they're so highly correlated, you in fact cannot separate them. We looked, analytically you have to separate them, but we looked at both lean mass and fat mass, and we found that the loss of lean mass by DEXA or by the CT was associated with mortality and little effect by confounders. And then what we did was we adjusted these for the weight loss. So the question is, can this just be simply recognized by a simple change in your scale weight? Is this idea of sarcopenia or loss of muscle mass with age something that is just moving together with loss of fat in a way that you just need a scale to pick it up? And we did find that the association only for the CT was independent of weight loss. And so what that's telling us is that people who lose lean mass that's sort of out of proportion for their weight loss, a failure to conserve their lean mass, are at higher risk for mortality. So I think this shows promise that following people's body composition over time is very informative. These are the hazards ratio. These are standardized for each measure so that they're kind of put on the same scale. And you can see that the associations for the CT scan measure were stronger than for the DEXA. And we think the reason for this is the DEXA's failure to eliminate the fat from the DEXA mass. Okay. So then finally we have this changing definition problem that is a well-meaning attempt to provide something that's clinically useful for saying if an individual person is sarcopenic. And the idea is that sarcopenia really isn't just poor mass, it's also poor muscle function. The problem with the low lean mass definition is that there are many people with low lean mass per height squared who are thin, who are fit, who are athletic. And I like to use the illustration of Gandhi, who was fasting and walking for miles and probably was quite fit, until he passed away. But the sarcopenia definition of appendicular lean mass per height squared would say that he is sarcopenic. And it would say that these women are not sarcopenic. And so the idea here was that, well, you don't even want to evaluate sarcopenia unless somebody is having poor function or disability. So if poor function is present, either low strength or low gait speed, then that appendicular lean mass per height squared could be used to define sarcopenia. So there's been several consensus groups now, an international working group, the European working group, the foundation of NIH, that they all start with either a low gait speed or a low grip strength or both. And then if the lean mass is low, you can call someone sarcopenic. And the idea here is that we need something. We need to agree on something so that we can begin to intervene and enroll people in trials or enroll people in studies that might even be observational studies, or to control for their body composition in some other analysis. Now, interestingly, the European Working Group does not recommend any particular way of measuring lean mass, and it does not recommend any indexing of that lean mass in their recommendations. But most use the appendicular lean mass per height squared. And then the FNIH recommends DEXA appendicular lean mass divided by BMI. And I showed you that before. That was based on a large meta-analysis and a regression tree analysis of what the best adjustment of lean mass would be to predict function. So here we have two very different approaches. I showed you how they're not correlated, and not well correlated, and there's a lot of uncertainty here about that aspect of it. If you look at this recent systematic review and meta-analysis of outcomes of sarcopenia, they decided up front that they were going to just take studies that use the appendicular lean mass per height squared, and they show nice, consistent associations for the most part with functional decline and mortality using that approach. But I think that careful scrutiny reveals that these associations that they see might actually be being driven by the poor function and not by the low appendicular lean mass per height squared. Low gait speed and poor strength are very strong predictors of disability and death. And sometimes these papers will separately break that apart, and when you look at it, that appendicular lean mass association is not strong. And it's there, though, but I think it's driven by the high correlation of appendicular lean mass divided by height squared with a low BMI. So it's finding your thin, sick, frail, older people. So is that really telling us about sarcopenia? And is that supporting the idea that muscle mass should be an intervention target? And I think that it's a mistake to continue to pursue mass as the target in sarcopenia when we know that the strength and the function seem to have a stronger association, and that fat is clearly very disabling to older people. So fat infiltration of the muscle, be it Hounsfield units or marbling fat, very strongly related to strength. It's strongly adversely affects function. I showed you before that the loss of strength outpaces the loss of mass, so there's now more focus on the strength itself with the term coined by Todd Manini and I think his name's Brian Clark, to separate that from the idea of sarcopenia. And in addition, the strength measures that are used do not often consider the speed of the force of the contraction, which is muscle power, and that declines even faster than muscle strength, and that tells us there's a strong neural component. We know that endurance, VO2 max, declines faster than the mass decline, so even resting metabolic rate and VO2 max are and they're not explained by cardiac output and pulmonary disease, that this aspect of the muscle function cannot be understood by just understanding mass. So the muscle fat, the intramuscular fat, I think is a very important target. This shows some pictures of some cross-sections of MRI of that marbling fat, but it's also the fat in the muscle tissue, the lipid droplets, and the metabolism. Here's a couple of things that we worked on in Pittsburgh where we looked at this intramuscular fat in, this was the LIFE study. The LIFE study was a physical activity trial, and we found that the people in the trial over time were gaining intramuscular adipose tissue, and we saw that in Health ABC, that no matter which way weight gain and weight loss are going, that this parameter increases steadily with age. It increases more in people who gain weight and increases less in people who lose weight, but it goes up. We were able to, in this add-on study to the LIFE physical activity trial, to abolish that gain in intramuscular fat with physical activity. And we also did another study of weight loss where we compared weight loss with physical activity to physical activity alone. Physical activity, and that stands for successful aging, so that was our control group. And with weight loss, that intermuscular adipose tissue was abolished even more so than just with physical activity alone. So it's very sensitive to interventions, and further, in another follow-up paper, it's related to function. And here's a very recent paper. I get to see these because it's advanced access in the Journal of Gerontology, and I'm the editor of the journal, and we were pleased to have this paper. It's a very small study, but it showed that the adipose tissue in the thigh, this marbling fat, has more senescent cell burden in the fat by this surface marker, P16, and that this higher levels of senescent cells in the adipose tissue, I'm not sure what type of cells they are, they didn't sort that out, whether they're inflammatory cells or whether they're adipose cells themselves, but they are related to function, and an intervention that decreased the adipose tissue and decreased the senescent adipose tissue that was related to the function. So I think that's an exciting new paper. A little bit more about dynapenia. This is the model in the an update paper that Todd Manini and Brian Clark published a few years ago, where they bring in not only the actual muscle itself, but the central nervous system as a whole as being important to muscle strength, and then all of these other aspects of the muscle tissue. It's been known for some time that as people get older, that there's a dropout of motor neurons, and the remaining motor neurons need to innervate more of the muscle cells. So you get a bigger, what's called a bigger motor unit with aging. And the way that this turnover in innervation happens results in a clustering of fibers with the grouping as the innervation changes with age and the loss of the type 2 fibers. So this is another important thing about aging muscle. And then the muscle energetics, we've been doing some work on looking at energy production in the muscle with magnetic resonance spectroscopy, where you can look at the recovery, basically, of phosphocreatine, which tells us the ability of the mitochondria to their oxidative capacity. And we found that this was related, this measure in the muscle. You have them exercise in the magnet, and it the rate of recovery of the phosphocreatine tells you about the ability of the mitochondria to regenerate the energy. We found that this was related to physical function, slow walking speed, and are hopefully embarking on a larger study soon that we have a reasonable priority score to do a cohort study with measures like this. So anyway, I thought I really shouldn't just complain about the literature and what's wrong with it and tell you what the right way to do it is, but there are continued efforts to define sarcopenia, but I think they're raising doubt about muscle mass as a major culprit in morbidity and mortality in older people. And I think it's very hard for people to let that idea go. But since you're a friendly audience, I'll tell you, I think that we need to stop looking there. And the reasons are this lean and fat coupling. Muscle and fat are so highly correlated that you can't really think about body composition in terms of one compartment or the other. I think there is lean conservation, so even though we see this failure to conserve lean in some people who are sick, for the most part, I think people and probably most organisms are designed for the fat compartment to be the variable compartment and not the lean. And so there is a lean conservation. And then the mass measures have very great lack of detail on the contractile elements, as well as the fat, lipid droplets in the cells, connective tissue. So I just don't think they're detailed enough. So we need to talk about aging muscle, and there have been some new terms that are in the literature now that focus on these aspects. Myosteatosis for the muscle fat, it's clearly important. Dynapenia for the loss of muscle strength and power. Whether it's mostly innervation or is it in the cells themselves needs to be worked out. The energetics impairment, I thought maybe Nick, you and I over dinner could come up with a term for that that was like one of these fancy Latin or Greek origin type names, with a need to focus on mitochondria, but mechanistic studies probably require muscle biopsy. And then these other aspects, external factors, disuse, the inflammation of aging is probably playing a major role, stem cell failure, et cetera, and the connective tissue function has been under study. So there is aging muscle. This is a picture of muscle biopsy being done in the quadriceps, and I threw this on at the end because that we have more opportunity to do this and are pursuing it. There are interventions. I believe in use it or lose it, and that aerobic and strength are both important. There's a tremendous need to target obesity. Older people have great difficulty carrying excess body weight in old age. A nice clinical trial published a few years ago in the New England Journal of Medicine shows that they can do it safely and improve function even if some muscle mass is lost. There's a lot of interest in nutrition. Probably really hot right now are essential amino acids. Elena Volpe, who you collaborate with, is really a leader in this area. The role of chronic inflammation is important. And I think most people would agree that the hormones have seen their day because they're targeting mass, and increasing mass does not necessarily improve function. So I hope to have the opportunity to continue to work with people here. Pittsburgh is a site for the molecular transducers of physical activity, and Nick leads the site here. I think this will give us, it's not meant to be a study of aging, it's meant to be a study of physical activity across the lifespan. But by looking across the lifespan, I think that we will begin to understand better this loss of function that occurs and the relative roles of the muscle and the fat compartments, because both are being looked at, which I think is very important about MotorPack, that there was a recognition not just to look at the muscle, but also to understand the fat. So I'd like to acknowledge my colleagues, my center, our Pepper Center in Pittsburgh, our Aging Institute, which is growing, and the funding that I've received from mostly NIA and NHLBI over the years. So thank you very much. Okay. More questions?